Okay, as we continue with these chapter summaries, we are now looking at statistical distributions, which is Statistics Applied Year 1, Chapter 6. And we're going to dive straight in with looking at probability distributions. Now, this chapter is a little bit strange because there's kind of like two halves to it. There's like this stuff to do with probability distributions, and then suddenly it starts talking about the binomial distribution. But we'll get that all tackled nice and easily. So just a quick little bit of background about this. When we use a capital letter in statistics, we are using capital letters for the whole distribution of possible outcomes that we have. And this is called a random variable. And actually it's a discrete random variable in A-level maths because we don't look at continuous ones. And so we'd usually use capital X and capital Y. If we use a lowercase letter, this is for a particular value of the random variable. So we'd use lowercase x and lowercase y here. So for example, the distribution of rolling a dice, the probability distribution, or the discrete random variable for rolling a dice would either be 1, 2, 3, 4, 5, and 6. And each of those outcomes, 1, 2, 3, 4, 5, and 6, would be represented by the lowercase x, but all of them together would be represented by that capital X. And distributions, as I've said, they can be presented in tables. And I haven't got a question on this, but if you do get asked about a discrete uniform distribution, it is one where all of the probabilities are uniform, i.e. equal. And so a kind of typical example of that is what I just said. When you roll a dice, a fair dice, I should say, the outcomes are 1, 2, 3, 4, 5, and 6. And it is a discrete uniform distribution because the probabilities of those outcomes are all 1/6. Obviously, it's discrete because you can only get 1, 2, 3, 4, 5, or 6. You can't get any sort of values that are in between. And as usual, the sum of all of the probabilities should be equal to 1. A bit like in the previous video when we look at Venn diagrams, we now are going to say that these outcomes are going to have to sum up to 1 as well. So they often like to do these probability distribution questions. They like to do it to kind of test your skills with probability. And so at the end of the last video, I said not drawing a tree diagram can often be a lot quicker, and you'll kind of see how that might be useful in this example. So this one says that Mr. Bison selects 3 letters at random, one at a time without replacement from the word mathematics. The discrete random variable x represents the number of times he selects the letter M. Complete the probability distribution for x. And it's been drawn for you. Now, if it wasn't drawn for you, you would be expected to be able to draw this table yourself, and you'd be expected to kind of reason that you could either get M no times, 1 time, or 2 times. Obviously, from the word mathematics, we cannot pick the letter M more than twice because there are only 2 letter M's that we have there. So it's been partially filled in. We already know that the probability of getting 2 is 3 out of 55. I think this one is going to be the easiest. So we're saying what is the probability that the outcome is equal to the lowercase value of x, which in this case is 0. So what this is really saying is the probability that the number of m's being picked is 0. So let's just quickly look at the word mathematics. We have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters, of which we have 2 M's. So there are 2 M's and 9 not M's. 9 not M's that we have here. So we're going to try and say what's the probability that when we're doing 3 letters being picked and not replaced, that none of them are M's. So if I want them to be not M, not M, not M, so I want no M's here. For the first pick, we would have to pick 9 out of the 11 to get something that was not a letter M. But for the second pick, there are now only 10 letters. And when we get to the third pick, there will only be 9 letters. But if we've also picked a letter that is not an M, one of those 9 not M's has gone, so there are now only 8 of them for the second pick. And then for the third pick that we've got, 2 of those not M's have already gone, so there will be 1 fewer than the previous, which means that there will be 7. Now you might think, oh, I want to draw out a tree diagram to visualize what's going on. I'm going to encourage you to try and do these questions without using a tree diagram. So when I multiply these out, I have the 9 elevenths times 8 tenths times 7 ninths, and we get that the probability of picking no M's is 28 55ths. So this probability is 28 55ths. Now, you might think of the shortcut of how to get this one, which I will come back to in just a second. I'll tell you what, we'll fill that one in right away. We've already said down here, didn't we? The sum of the probabilities is 1. So if I want to find out what this probability here is, I can just do 1 minus 28 55ths minus 3 55ths, and it will give me that probability. So I will do 1 minus that minus 3 55ths, and we get the probability of getting 1m is 24 out of 55. Now, if you wanted to work out the probability of getting 1m, I will do it very, very quickly. Okay, 1m, we would have to pick an m on the first go, possibly on the first go, so that would be 2 out of 11. There'll still be a 10 and a 9 for the other parts because we've got one letter less each time. But because we only picked an M here, there are still 9 not M's, and then there would be 8 not M's because one of them got picked on the second go. Now this, if I do my 2 11ths times 9 tenths times 8 ninths, I get 8 55ths. I don't get 24 55ths. And this was because I did M, not M, not to m. And if you think about the order this could have happened in, that m could have been in one of those 3 places. So we would also need to multiply it by 3, which gives us the correct answer of 24 55ths. So just worth thinking about how you can do this. The extra thing here was we needed to triple it because that m could have been picked first, second, or third. Anyway, I'm going to do a sort of little scribble through that because we didn't actually need it. We were able to do it in a much quicker way over here. Next question. In a video game, a player can either win 0, 1, 2, or 3 coins for a particular action. The random variable y represents the number of coins won and has the following probability distribution where a and b are constants. And the first thing it says is given that the probability of winning at least 2 coins is 2/3 the probability of winning 0 coins, find the values of a and b. So I'm actually just going to go straight in with this. The probability of winning at least 2 coins would be the a plus a 0.05. That's the probability of winning at least 2. And they've said that that is 2/3 the probability of winning no coins, which is 2a. So I've got a nice equation there that if I solve it, I can find out my value of a. So a plus 0.05, 2 times 2/3 is 4/3 a. I'm going to subtract a from both sides so that I get 0.05. 4/3 minus a is going to be 1/3 a. And then I will triple both sides so that I can go that a is 0.15. So if I go to my table, and I'm just going to kind of jot this down underneath it, this one is 2 times a. 2 times 0.15 is 0.3. This one is 0.15, and then we have a 0.05 over here. So if I want to now find out the value of b, well, I can just say that b is equal to 1 minus 0.3 minus 0.15 minus 0.05, because they all need to sum to 1. So that's 1 minus 0.3 minus 0.15 minus 0.05. So that is that b is 0.5. So I found out my value of a and my value of b here. Okay, now for the next part of the question, for part B, it says, given that each outcome is independent of previous outcomes, calculate the probability that a total of exactly 2 coins is won when completing the action twice. So we're now going to be sampling from this probability distribution twice, because we're doing it twice, and we want to find out the probability that the total is going to be 2 coins. So we need to think of all the ways that we can win 2 coins. Well, I think the first way that jumps out to me is I could get 1, and then I could get 1. On the first go, I could get 0 coins. On the second go, I could get 2 coins. Or on the first go, I could get 2 coins. And on the second go, I could get 0 coins. So I'm just going to use this distribution. Let me just put this 0.5 so it's a bit neater for me to actually see what it is. I'm going to actually calculate these probabilities. And because it's getting a 1 and a 1, we know it's going to be a multiply. So that would be b times b, or 0.5 times by 0.5. And for 0, then 2, well, 0 is 0.3 and 2 is 0.15. So that's 0.3 times by 0.15. And actually 2 times 0 is going to be the 0.15 times by 0.3. It's the same as this, but we've got them kind of written in a different order. So I'm going to be a bit lazy, and I'm just going to multiply that by 2 to represent that there's both of those. So what I'll do is calculate these. 0.5 times 0.5 is 0.25. And 0.3 times 0.15 times 2 is 0.09. So the probability that they get a total of 2, probability of total of 2 coins, we're just going to sum those together to get that total probability, which is 0.34. So the probability is 0.34. Now they could have asked something else. Instead of it summing to 2, they could have said summing to 3, which maybe would have been a little bit trickier. You would have had to do a 1, 2, a 2, 1, a 0, 3, and a 3, 0. Maybe a tiny bit trickier, but not that crazy. Okay. So now we move on to a very particular type of distribution, which is a binomial distribution. Now we're going to do some kind of abstract stuff here, and then we'll move on to a worded question in the next part. But hopefully you remember what the binomial distribution is. We write it like this, that x is distributed as the binomial distribution where we have n trials and a probability of p here. So x can be modelled with the binomial distribution if there is a fixed number of trials, which is n, there is a fixed probability, which is p, the trials are independent of each other, and there are only 2 outcomes, success or failure. So it wouldn't work for something like win, draw, or lose, because there are 3 outcomes. It would only work for a game where it's either like win or draw. Now, this part is in the formula book, okay? This is in the formula book of how you calculate the probability. It looks really complicated. It's actually not that crazy. So we're saying, what is the probability that our outcome is x? And x could be just one of those outcomes that we had in a table. It's literally just representing a number. So we'll come back to this part in just a second, but let's say that there were n trials and we wanted x of them to be a success. Well, the probability of success, we would be multiplying that by itself x times for all of those successes. 1 minus p is it not being successful, and that would be n minus x. That's the remaining number of trials that there are where it would fail. So we've got these x successes, the remaining ones as fails, and this n choose x, this binomial coefficient that we have here, that will deal with the fact that there are often lots of different combinations that still give you the same outcome. A bit like here, we had the 0, 2 and the 2, 0. It's like that 2 is the same kind of thing as this part to count for the fact that there are different orders that this can happen in. But of course, you don't have to use this. In fact, this is very rare to use this. You can also find this on the calculator. We maybe would use this if there were some unknowns, but that's incredibly rare here. And then last of all, we need to calculate cumulative probabilities. So we're saying, what's the probability that x is less than a or greater than a, or this one here. Now, the one I haven't included is the probability that x is less than or equal to a. That is literally just the cumulative distribution mode for the binomial on your calculator. So that's the easiest one to find. Nothing needs to be changed about it. Now, if I was going to say the probability that x was less than a, well, we would change this so that it's actually the probability that x is less than or equal to a minus 1. It's often a bit easier with numbers. Like if you imagine that we're saying the probability that x is less than 3, that's the same thing as just saying that x is less than or equal to 2. And probability that x is greater than a, well, for that one we do 1 minus the probability that x is less than or equal to a. Okay, again, if you think about that with numbers, the probability that, say, x is greater than 3, that's the same as saying it's like 4, 5, 6, all of those values. So it's like doing 1 and you're getting rid of all of the ones that are less than or equal to 3. So that's why you have this part and this part staying the same here. I actually think it's kind of a bit harder with letters than it is with numbers. And then my last one that I've got here is the probability that x is greater than or equal to a. That is 1 minus the probability that x is less than or equal to a minus 1. I need to check that with numbers. So if I had the probability that x was greater than or equal to 3, that's saying it's like 3, 4, 5, 6. Yep, I've removed from it, I've done 1 minus the probability that x is less than or equal to 2. I've got rid of the 0, the 1 and the 2, which is represented by this part that we've got here. So I've done those correctly. And like I said, I actually find them a lot easier to do with numbers rather than all these kind of crazy letters. So we're actually just going to go straight in and do some calculations for these. Now, I personally have the graphics calculator, so I pretty much stay in the CD mode the whole time, the cumulative mode. But on the non-graphics calculator, this first one we would do in the PD mode, the probability distribution mode. CD is for cumulative. So I'm actually going to do part A. If you do it on your calculator, you will get the answer straight up. But I'm going to do it using the formula just to kind of demonstrate how we would use this. So we're going to have n in this case is 20 and p is 0.4 and x is 8. So our probability that x is equal to 8, I'm going the long method with this, will be n choose 8, we're going to say that the success probability is 0.4. We want that to be successful 8 times. The failure probability is 1 minus 0.4, which obviously we know is just 0.6. So I'm going to multiply that by 0.6, and n minus x is how many times we need it to fail. Well, there are 20 trials, 8 of them are successful, which means 12 of them are failing. Now, I'll just do 20, choose 8 on my calculator. That's a big number, 125,970. I'll times that by 0.4 to the 8, times by, 0.6 to the 12, and we get 0.1797. I'm always going to be going for sort of 4 decimal places for these questions. Now, if you did just do it on your calculator, you would come up with the exact same thing. You would put in your x value is 8, number of trials is 20, and the probability as 0.4. And I'm just confirming I've done it right. Yep, you do get the same thing for that. Okay, so for part B of the question, I'm saying that x is less than or equal to 3. That one you can just go straight into the calculator, the cumulative one, and you should come up with the answer to 4 decimal places of 0.01596, or to 4 decimal places, 0.0160 to 4 decimal places. Now, if you have the graphics calculator, you can actually do the probability that x is greater than 9 very easily. You can just say greater than 9 is greater than or equal to 10. So you could go straight in and put 10 as your lower and 20 as your upper. But if you don't, greater than or equal to 9, we're talking about 10, 11, 12, 13. We are removing all of the ones that are 9 or less. So we'll do 1 minus the probability that x is less than or equal to 9. Now, you could skip both of these lines if you didn't have the graphics calculator, if you do have the graphics calculator. So let me just quickly work this out. So I'm doing less than or equal to 9. So it's 1 minus 0.75533 like this. So that's 1 minus 0.75533. That is 0.2447 to 4 decimal places. Just going to double check that that is what I've actually got on the calculator, greater than or equal to 9. Yep. Okay, and then last of all, part D that we have, the probability that x is greater than or equal to 5. Well, we're really talking about 6. Oh, no, we're talking about 5, 6, 7. So we're removing all of the ones that are less than 4. So that's the probability that x is less than or equal to 4. Again, if you have the graphics, go straight to it. You could just do between 5 and 20. But I'm going to pretend I don't have the graphics calculator, and I'm going to do 1 minus 0.05095. 1 minus 0.05095. 4 decimal places is 0.9491. And I'm double checking that that is correct. 0.949. Oh, I think I've maybe not written down enough decimals for this. Sorry, guys. 5095195. So when I actually do the subtracting, 4 decimal places, it's 9490. So 9490. Now I know that's kind of annoying. If you had a graphics calculator, I hope you have just zoomed through that bit, because it is very, very easy. Okay, sometimes we need to find out missing values. So it says, given that y has a binomial distribution with 25 and 0.3, find the largest value of a such the probability that y is less than or equal to a is less than 0.05. Now this is where you can use your calculator, but I personally find the printed tables very, very useful for this. So I'm going to have a look. I've gone to the section of the formula booklet where the probability is 0.3, the number of trials is 25, and we have these cumulative probabilities. They're always telling us the probability of this value or less. So 0.6769 represents getting 8765432 or 0 all added together. So this first part, we're saying the probability that y is less than something has got to be less than 0.05. Well, this is really easy. We just look down the list. The first one that is less than 0.05 is this one. We're looking for the biggest value of a that makes this true. So if I wrote down the probability that x is less than or equal to 3, that is 0.0332. and the probability that x is, and that's obviously less than 0.05. I know I can just see this from the table, but if I wrote down the probability that x is less than or equal to 4, which is 0.0905, that one is greater than 0.5. So clearly, just by looking at the table, a must be equal to 3. That's the biggest value that keeps the probability less than 0.05. Now for part B is a little bit difficult, right? We're saying the smallest value of a, such the probability that y is greater than a is less than 0.05. And this is where I want to talk to you about how we understand this table. So for example, this 0.8106 is telling us that it is 9 or less. So if I was going to kind of say the opposite of that, so I'm saying the probability that x is less than or equal to 9 is 0.8106. If I was going to kind of do the opposite, the probability that x is greater than or equal to 10, it's the other part of the table. It's actually the 1 minus that. And 1 minus 0.8106 is 0.1894, 0.1894. So what I'm trying to show you here is you can read the table that this value is this one or less. If you do 1 minus this, it's the other value 1 above or more. So let's have a think from our table. If we're saying that it's got to be less than 0.05 for it being greater, I'm going to look for something that is greater than 0.95, the first one that goes bigger than 0.95. So let's get rid of all of this. It's not that helpful. So this part is 0.95. So we're saying that 11 or less is 0.9558, which means that 12 or more will be the first one that goes below 0.05. So I'm going to just write down the probability that x is greater than or equal to 12 has got to be 1 minus 0.9558 from the way that we read the tables. 1 minus 0.9558. Which is 0.0442. That's obviously less than 0.05. Now, there's not any point of going lower than that, because if I did the other one, which is the probability that x is greater than or equal to 11, that would be 1 minus the probability of this one, 0.9022, which is obviously going to be bigger than 0.05. That is 0.0978, which is bigger than 0.05. So this is the one that we want to use, okay? This is the right one. We just need to change the probability that x is greater than or equal to 12. That is equivalent to the probability that x is greater than 11. Greater than or equal to 12 is 12, 13, 14, 15. Greater than 11 is 12, 13, 14, 15, which means that our value of a in this case is going to be 11 because of the fact this question doesn't have the or equal to sign that goes with it. Maybe I've gone into a bit too much detail there. I hope, though, this sort of discussion of the table might be something that's useful for you. So we're going to finish off with this last part, which is about binomial within binomial and just worded questions in general that we have here. So it says here, the first part of a question may ask you to calculate a probability that is used within another binomial distribution in that same question. So let's have a look at this. It says that Alice enjoys going bowling. The probability that she scores a strike in a single bowl is 0.24. Alice bowls the ball 10 times per game. Calculate the probability that she gets at least 3 strikes. So I'm actually going to do something you don't have to do in the question, but I'm going to say here, I'm going to let x be the number of strikes scored. So we now can say that x is going to be a binomial distribution. She is doing this 10 times, and the probability that she gets a strike is 0.24. And the first thing we want to do is the probability that x is at least 3, greater than or equal to 3. That's the same as calculating. Remember, that's 3, 4, 5. We're actually getting rid of the less than or equal to 2. But I'm going to save me some time. I have the graphics calculator. I can actually just do greater than or equal to 3 on my calculator straight away. So greater than or equal to 3 is 0.4442 to 4 decimal places. Great. And then part B of the question is the same distribution. We're going to calculate the probability that she scores no strikes. So we're trying to say the probability that x is equal to 0. I can just go straight to my calculator and calculate that straight away, and I get 0.0643 to 4 decimal places. And then this is where it gets interesting, because it says that Alice intends to play a game of bowling once per month for an entire year. So she's going to play 12 games of bowling in this year. Calculate the probability that Alice scores at least 3 strikes in at least half of these games. So we're now no longer talking about how many strikes she gets in a game. We're talking about how many games of these 12 games will she get at least 3 strikes. And this is the binomial within the binomial part that we've got here. So I'm going to write down, let y be the number of games where she scores at least 3 strikes. And so this time, y is going to have a binomial distribution. She's going to be playing 12 games across the year, and the probability that she gets at least 3 strikes, we've already worked out earlier in the question, it's 0.4442. And now we can say, well, what is the probability that out of these 12 games, it's at least half of them that she gets at least 3 strikes? So we're saying, what's the probability that y is greater than or equal to 6? So it just becomes a matter of putting that in your calculator. Greater than or equal to 6 is 1 minus the probability that y is less than or equal to 5. But I can do it on my graphics straight away, so I will do that. So I'm saying greater than or equal to 6, and there are 12 and 0.4442. Don't worry about the fact that I've used a rounded version of this. Mark schemes would allow for that. And that is 0.4567 to 4 decimal places. Okay, I'm going to jump over here for part D of the question, which says to calculate the probability that Alice scores no strikes in exactly 2 of these games. Now, again, you don't need to write this out, but I'm going to say let Z be the number of games where she scores no strikes. So this time, I'm using a new letter because it's got new distribution. It's a binomial distribution with 12 games. The probability she got no strikes was 0.0643. Again, we don't mind that we're using the rounded version. That would be accounted for in the exam, in the mark scheme. And we're going to calculate the probability that she scores no strikes in exactly 2 of these games. So if you don't have the graphics calculator, you jump to PD mode. If you do have the graphics calculator, I will just put the lower and upper as 2. I'll change the probability to 0.0643, and I get to 4 decimal places, 0.1, if I can write properly, 0.1404 to 4 decimal places. And then to finish off, it says criticize the use of the binomial distribution to model Alice's scoring. Strike scoring. Well, we need to criticize one of these things that we've got. Fixed trials, fixed probability, independent trials, 2 outcomes, success or failure. So there are a fixed number of trials. We can't criticize that. There are 2 outcomes, success or failure. We've been told that the probability is fixed. So usually it's going to be something to do with independent. It is unlikely that the balls that she throws, the balls that she throws are going to be independent. Maybe if she does well in one of the games or in one of the throws, it might influence how well she does in the next one. So I'm just going to say something. It is unlikely that Alice's bowls are independent of each other. Meaning that, you know, if you've ever played a game of bowling and you do really well, you tend to keep doing really well. There's like a psychological aspect to it as well. And maybe if you bowl the ball and it's always going into the gutter, you're probably more likely to keep going into the gutter because maybe you're not, maybe you're getting into your head about stuff as well. So it's unlikely that they are independent of each other. That would probably be a good criticism for this. So this is going to continue. It won't be any of this kind of probability distribution stuff, but the binomial stuff will definitely be continuing in the next video where we have a look at binomial hypothesis testing. So I hope to see you in that video.